Okay.
You just have to click OK.
Yeah, it's not easy because the mouse disappears in this mode. Look how it's the same. Thank you. Okay.
Okay, so it looks like people are here, so I say we can start from timing. So Francie will continue.
Okay, so let's continue this series of lecture on quantum information and computation. So, about quantum technologies, the economist point of view means that one fact that is sure that today there is plenty of money invested in quantum computing. Everywhere, one can see that there is investment in terms of states and also floraison of companies and startups that emerges. And what's interesting is that each company has their paradigms. So that this company believes in atoms, this use electrons, the other use photons. Not all the company use the same technology that they believe will be the one that builds the quantum computer. But all of them are emerging. All of them have advances and properties and charts and how many qubits they do and what's the fidelity and what they can do, what they can do. Here is from 2022, saying, okay, they did 5,000, this is the name of the companies, depending on the technology, you see that they advance. There is clearly no, I mean, it's not yet something that's, nobody will tell you this is the technology of the future, but everything that is small behaves this way and reality tends to support it. I mean, the question is, how well will we be able to harness, to control, to maintain in coherent sense, these will be able to control more easily photons or electrons.
How do these companies actually make profit, or is it just a long-term thing, or do they hope that some bigger company buys them or something?
No, it's with money. I'm not a good economist, but people invest money because they think they will win money, and people are still investing, and money is still pouring, and still having great announcement and
profit that those making they have to buy.
Yeah. For example, for the states, I mean, for example, for example, for the French government, in the plan, we buy one quantum computer per year with different technologies to be sure to have and to be sure to support, and many things do the same. Some built over the net. I mean, the 2 qubits computer, I have received emails. It's not that expensive. I don't remember. It was for 2 qubits, it was like 10,000 or something like this. How do you have a real 2 qubits? I don't know if it was real. I don't know the company, but people are selling. I don't know. But just as an example, Scott Aronson, who's a computer scientist but worked with AI and with quantum and has an active blog about the subject. Very recently, in one day, in November, you see already that many companies announce results and advances. He said, okay, be careful of Oxford Ionics. This Elias presented something like this, new device, new fidelity. So it's what I was saying. For us, what's undeniable is that technology is advancing in all the directions and things are improving, and it seems plausible that they will do it. It's of course, nothing is one, but the direction of the economy is this one. Okay. Now, what's the physicist point of view? For this, I will go fast. It's a talk it's from a presentation given by a physicist. So this I know, but some parts I will not be able to answer all the questions, but you can try me. So the physicists say, okay, to build a quantum computer is not just the device that is quantum, it's a whole pile. They will have the chip, the quantum to classical, and architecture below, the cryo, because usually most of them, they don't like room temperature. So there is electronic control that changes the energy, and it's a whole conception pile that is above the idea of what we manipulate when I say I apply a unitary. In fact, is hidden behind a whole layer of implementation of how to imply this unitary. And how to imply this unitary is even worse because different technology implies different constraints. So, for example, for here illustration with different technology and the representation of where the qubit will be, where the information that was at the transistor level there is not current. Where will I put my information? Where will I put my bit of quantum information in which small coherent system? And all these are ones that are working at some level. I mean, they have a good fidelity. All of them has some problems, some for transport, some for communication, some for measure, some for unitary, the other for multiple bits. But, okay. Let's go, it's just to give the physicist point of view of the duality between wave and particle. The way physicists view things is, okay, I want to run an interference, so I'm repeating an experiment, and I'm saying it's the same device, it's doing the same thing, I just need to do plots and to count. That's the only thing they need to know. They need to count. And they say, I'm doing the same thing, it should be the same thing, the environment didn't change. So at one point, they have a curve. Different devices means different experiments, but at the end, it's just a curve with points that they have. And then they have a law that says, okay, how does the state evolve? I told you that evolved with a unitary. In fact, physicists like a lot the Hamiltonian, which the derivative exponential of IH gives the unitary. So they say, okay, what's the rule of evolution of the unitary? And with small timelines, it will be linear, more or less. And I can decompose in two parts, imaginary and I can sum up, and I have this curve. And to see this curve, what they do is, they don't have this thing. I mean, they say this is reality, but what they do in practice is they have slots, and they count what the observation. So it hits on this place, so I have the ball, and it hits something else. And they put the real experiment is just counting, and saying that, okay, this counting looks like this curve. So I have a nice equation. So physicists say, yeah, the reality is what we want to see. So it's the limit of identical self-reproducing process. Okay, now this curve, I identified it as the waves. So, okay, I can see it in many phenomena, and you can in water outlets or in guitar and sounds. And they act on it. So they say, okay, I can act with different frequencies, and I can define energy, and they have formulas for waves, and I want my theory to be correct to see these are the objects that I will manipulate. So for the electron, they say, okay, I want to estimate the position, so I will define, is it far or is it close to the nucleus? And they will say 0, it's close to the nucleus, 1, it's far from the nucleus. Has it been extracted? So I will define two states. And the experiment, they will stack things, they will adapt notion, they called amplitude frequency, and they, with playing with the parameters, they obtain patterns like this. And they say, oh, okay, I changed my parameter, I arranged this thing, and it looks like an interference. Why? Because there are white places and there are brown places. So, okay, I have interference. So that's the quantum bits. Okay, I say, okay, I change my devices, I change my way to act on it, and they have other patterns of interference. The holes are in other place. In the first place, the hole was there, now the holes were there. So I have another basis and another measurement. I can have different level of excitation because I can say they can go even further from the atoms, they can go further from the nucleus. So I can define spin, I can define polarization here. So I say spin +1/2, -1/2 to maintain an average on 0, to have an expectation that is around the nothing. And in fact, they build devices with the qubit, for example, and this is from Grenoble, the qubit is some superconductor thing. So, no, Grenoble was semiconductor, so I don't know what this is, but basically they put this, they say this is the qubit, this is the communication, and this is the implementation on a circuit of what we will manipulate to have many qubits. Okay, you imagine with all these layers that what was true for all day computing and nowadays forgotten, because errors were there in the beginning when there were real bugs for the early days of computing, and now it stays important for communication, but it's no longer considered for computing. It's small enough to be negligible. And if your friend asks you why my computer doesn't work, the usual answer of the computer science is just reboot your computer and don't try to understand. So, okay, there are different systems with different constructions, different proposal. That's why there are companies, that's why there are millions, because they need to build all these things, all this white room, all these cells to check the fidelity, to say, I can have do better. So this is all the race now. They go for very low temperature for this type of technologies. So what's next from us to remember, unless you want to become a physicist to build a computer, in which case I'm not so good at the point it could be, you have to look elsewhere. I'm not an expert. So what needs for us to know is that noise is inherent to the technology. So you cannot build this type of things hoping to have exactly your qubit. And if we want to, the description of the state is with complex number, we want it to be analogic because we say the state is in the wave, then it's very sensitive. It can have many types of error, and I am already, it's hard to correct normal ones, so how can I do it? How can I do correctable computation if my computation has error that could be complex, if I cannot copy my states? It looks really unlikely to harness the control to make it still make sense after manipulation. And the reason why the domain states is that it's possible to do quantum error correction. And this is what I will explain to you. So quantum error correction, the principle is very simple. I mean, in classical, it's everywhere in communication, in your phone and in satellite communication, because we don't have enough control over long-term sent messages. We have to be able to correct errors there, even in the classical way. So the message that is transmitted gets changed by the environment, and the decoder, when he tries to read it, the sentence doesn't make sense. If he said, I want to understand quantum computing, what's he saying? Okay, either you do, I didn't understand, can you say it again? Because you are the end user of formal language and you don't have an error correction, the sentence has to be correct. Or you say, okay, I know more or less what you wanted to say, I can correct it by myself, and I can say, you wanted to say quantum computer. And I consider that everything around this is. What did I do? Implicitly, what I do is instead of doing, I reject, I correct it, and I change it, the sentence without sometimes even telling you. I interact with you not with what I heard, but with the correction of the version to make it make sense too. So, how do we do error correction classically already? Because as usual, everything was built with a strong classical inspiration. Say, we know how to do it classically. Quantum use classical as basis. So let's try to copy and let's to see how to deal with errors. Sometimes we fail. We have seen when we were trying to solve the problems of finding of the trivial salesman. But sometimes we work. It works. We have seen it for finding for the groovers. So let's see step by step. The basic scheme is the repetition code. Because if I send 1 and I send it by encoding it by repeating 3 times the signal, when I receive something, if I have 101, I know that it is not a code word. What is a code word is a valid encoding. So instead of using the 8 valid bits sequence of 3 bits, I'm using only 2 opposite corners of the cube. So I'm using only the all 0 bits and the all 1 bit. So if I have something else, I don't have a logical bit, but I have a bit with an error. I know it because it's not a valid encode. Why is not a valid encoding? Because the second bit is different from the other, and my code space was preserving all the qubits are the same. Okay, now that we did error detection, we can try to do error correction. And error correction is, okay, I received 101. The most likely code word was 111, and 1 bit was. Okay. Can we do same quantum? Let's say, for example, let's suppose that I can have a bit flip over my cube. You remember we have discussed different operations, different gates, and we had the Pauli X, the Pauli Z, with X flip, Z flips. We had the Adamov that turned 0 to the superposition of 0 plus 1 over square root of 2. But maybe my channels, and it's true for cat state or some, I mean, there are technology for which really there is one error that is more likely to happen than the others. But let's say for the sake of argument that the only physical error that could happen is an X on my channel. Can I correct it? By linearity, I mean, I am submitted to quantum rule, but the error also is submitted to quantum rule. So the error, if it acts on alpha 0 plus 1, alpha 0, 0 plus alpha 1, 1, it will flip, so it will change my state to alpha 0, 1 with alpha 1, 0. I mean, please don't hesitate to interrupt me and to ask questions. If I go too fast, really interrupt me. So you remember when we have multiple systems, the composition was done by tensor product. So we have, if my state was 0, then my state is 0, 0, 0. If my state was 1, I can put 1, 1, 1. So I can define what's called a logical state. So a logical state is a 3-qubit state. You remember a 3-qubit state is a vector that lives in a space of dimension 8. Because the valid state is the superposition of any of the 8 basis states. So the logical state uses only the 0, 0, 0 and the 1, 1 part of the space. Okay, if you remember, we have the CNRS that was a 2-qubit gate. What does the CNRS do? It flips the control bit if the target bit if the control bit was 1. So 0, 0 maps to 0, 0, 0, 1 maps to 0, 1, 1, 0. This one was the one it has 1, so I flip this one, I switch 0, I apply X, and this is what happened. Okay? So let's see how can we mimic the repetition code. So I want to mimic the repetition code, so to change alpha 0 plus beta 1 to alpha 0, 0, 0, 0, 0 plus beta 1, 1, 1. How can I do that? I start with plus 0, 0, I do a C0 and then a C0. What happens here? The first state is psi 0, tensor 0, tensor 0. Then I apply a C0. What the second state will become? I say if, but it's really a linear superposition. On the part where the first qubit was 0, nothing changed. On the part where the first qubit was 1, the second split. Okay? And then I do the third one, do the same. So, okay, this circuit implements the encoding for what circuit I want to move this one to this one, given to ancilla that I have the state 0. So it's possible to have this circuit. Okay. Now measurements. Remember, we have measurements. One formalization of measurements, a family of interesting measurements, is defined by just I use projector that cover the whole space. So I have orthogonal projector. What does it mean? That if I take 2 times the same one, I have pi times pi is equal to pi. Pi times pj is equal to 0 because they are orthogonal. They stand with the identity So it allows to recover, to describe how we obtain the Born rule that we have seen before by doing just projection into the orthogonal. It explains also why I keep only the coefficient on the space on the part that survives. That's what you have seen before. So you've seen that exactly what we have done was projecting on one or possibly a subspace here. So the state is normalized after the measurement so that it becomes on the projected subspace. So iteration will be consistent. Okay. I don't know if you remember. If I have this state, it projects on the state 0, 0, 0. Why? Because matrix multiplication is associative. So instead of looking at it as a matrix, I can look at it as a vector with a line vector. So when I multiply with another state, I will have the scalar product on the right. And the only part that survives is the part that is 0, 0. So this is the projector over 0. This is the projector over 1, 1, 1. And this is the projector over this subspace. So when you write it, if you have a psi that has coefficient over all 3 qubits, this is a split of the whole space. Any state will have coefficient over these 8 basic states. So if I apply P0 plus P1 plus P2 plus P3 is exactly the identity. So I have really decomposed my plane, my space, into 4 possible cases. Okay. Let's see this operation, how it is a projective measure because it sums to identity and all of them are projectors. So if after the projector I have 0, P0, 0 projects there. So if my state was the logical state, alpha 0, 0 plus beta 1, 1. What will happen when I measure? What will happen when I measure if I do this one? You see or not? No, because we get one of the outcomes. This measurement has 4 classical outcomes, 0, 1, 2, or 3. And in case the classical outcome is 0, my state is projected into P0 psi. And the norm is the norm of this projection. So here, my state lives in the subspace onto which P0 projects. So it has 0 probability to give 1 because it's orthogonal to both the states that span the space. So when I measure these states in the normal basis, the probability of having the classical result 0 is 1. Okay, but now suppose that for some reason I don't have psi 0 and the second qubit was flipped. What will happen when I measure psi tilde, which is alpha 0, 1, 0 plus beta 1, 0, 1, beta 1, 0, 1? Is it clear or not? Exactly. This will give the probability 1, the classical result 2. And what's really surprising, you remember, one phenomena that happened when we do quantum measure is that the state is changed by the measure in general. Because it's reduced from it can be in what I can see. But if it's already in one of the subspace, it will not change. So no matter whether the state's exactly this one or this one, the state after the measure didn't change. furthermore, the correction is possible. Because if I apply x to the second qubit, you remember x flips 0 and 1, everything is linear, so on this sum, it will move me back from this one to this one. Okay, so when I measure, I can get as a result, yes, just applying x to the second qubit means I don't touch the first, I don't touch the third, I apply x only on the second qubit. And when I apply this to second, I'm back to the encoded state. So if I measure and I get 0, I have nothing to do, I'm happy. If I measure and I get 2, I just need to apply x on the qubit 2. Okay, you see then that I have an error correction procedure that can be seen easily by interpreting now to what the projection means. What are the name of these 4 subspaces? They are all the same. First qubit is different from the other. Second qubit is different from the other. Third qubit is different from the other. And now you see that the projection is giving me this information. It's splitting onto these 4 subspaces that span the whole space. Okay, yeah, of course, I mean, with 1, 3, okay. So now, okay, but you can tell me, you can never suppose you need a lot of assumption to say the error has to be x. It could be something else. For example, it could be z. You remember what was the z gate? The z gate, it maps 0 to 0 and 1 to -1. What does it mean? It means if I have alpha 0, 0 plus alpha 1, 1, I will become alpha 0, 0 plus alpha 1 minus alpha 1, 1. It means that it's the phase between the 0 and 1 that is acted on by the operation. It didn't change the amplitude of 0, but it changed the phase, or the relative phase of the 1 compared to the one of 0. Okay. How can I do that? Okay, you remember that, of course, you have to think that I took the sphere and I put like this and I put it in a strange deformation to forget about complex number and to suppose that I have only real amplitudes to do everything on the circle. But it works the same. But plus and minus, plus is 0 plus 1 over square root of 2, and minus is 0 minus 1 over square root of 2. So, and plus and minus was also a valid basis of my sphere. As I was asked, I mean, I could consider just another basis and I would have been happy. It works the same. There is no reason. But then, how does the Z gate act on X and minus? The Z gate changes 0 to 0 and 1 to -1. So by linearity, it changes plus to minus, and minus to plus. Okay? No? Could I explain more? But it's just the Z is acting for the plus minus. It acts as a bit flip. It's a phase flip because I was looking at 0, 1. But if I look at it from the plus minus point of view, then it's just a phase flip, a bit flip. But I know how to correct bit flip. So let me do this. Let me do a base change and apply Hadamard. And instead of putting 0 as 0, 0, 0, 0 plus 1, 1, 1, I encode 0 as plus, 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 and 1 as minus, minus, minus. If I do this, then I am resilient to phase flip. Why? For exactly the same reason. I mean, I take as projection the one that does like this. They span the whole space, they are projector, it's really the same principle. It's just, instead of being different on the 0, 1 basis, now it's being different on the plus minus basis. Okay, can I do it with the circuit? I do the C node, and then I do the Hadamard. Because I ended. You remember, before doing this, we were on 0, 0, 0 plus 1, 1, 1. If I do the Hadamard, the 0 will become plus and the 1 will become minus. So I will have exactly what I want. So exactly on the same way, I could correct a channel on which only the errors happen by just measuring up with this projector and correcting depending on the result of the measurement. Okay, as I told you last time, physicists hate this type of stuff. They always want to manipulate at most 2 qubits at the same time because it's already hard enough to put them close together and to act on them without affecting the environment. And I was presenting projective measurement on 3 at the same time. Okay, it's valid mathematically, but can I change a bit my setting and rephrase it in terms of 2 qubit measurement so that the experimentalists are happy? And there is no problem. The question is, what I wanted to know is which one is different from the others. And among 3 persons, if one is different from the others, I can do it by asking 2 consecutive questions. So I can first measure the first qubit 1 and 2 to decide if they are on the same standard basis or not. And no matter what the result is, I will measure 2 and 3 or 1 and 3. And I will consecutively, I will be able, by doing my 2 qubit measurements, be able to conclude. Okay, I put more detail than that. So okay, if I do the first measurement, the state is projected. We have seen what happens. It's projected, so the state becomes on the Gutzak space with what probability? With the Born rule, which is the norm of the projection, which is the sum of the square of the amplitude of the ones. So if I want to write the state properly, when I did the projection, if it goes to 0, 0, and if I get the result 0, my state becomes 0, 0 plus 1, 1. Here I just put the Born rule as they were defined before to say, okay, even if the system has 3 qubits, I can measure part of it and I will project, and I know how to compute the projection. And it's exactly the same. The equation is the same. Huh? It's just that the matrix, you have to see it as this is applied tensor identity on the third system. So it's always an 8x8 matrix. It's just that it is a 4x4 matrix tensor identity. So the third system, I don't need to look at it by linearity. I will sum for different values. Is it okay? It's just in principle, instead of comparing them 3 at a time to say, is one of them different from the other, I can compare is 1 like 2 and then is 2 like 3, and I will get exactly the same information encoded in 2 bits. And if they are all the same, I will get 0, 0. If the third is different, but the one like 2 will be 1, 0, and 3 will be different. It's a trivial exercise to see how this split by 2 encode the same. Okay. Yeah, and it's the same. Note that the same principle will hold. It means that if my state, whether it has no error or 1 error, no, the projection will never destroy its information. It will still live with the same amplitude. I did a measure that gave me the information without destroying the amplitude, because I put it in a much bigger space. Because I'm not using the whole space, I put it in 2 corners of a cube, and I'm saying now, let's measure the whole system together. Okay, but in general, what happens if I have a general error? A general error? What's interesting is that I have a basis for 2 by 2 matrices. Identity xz and xz is a basis for 2 by 2 matrices. and everything is linear. So any error can be decomposed into some part on identity, some part on X, some part on Z, and some part on X. When I apply it, when I measure, it will be projected into one of them. So I need a correction scheme that is able, but at the same time, to deal with all of the cases. And this is possible. Okay, maybe it's not that easy to come up with, but it's called the show code. It's the same show that was doing the operation. And the idea is that the same thing. It says, okay, let's first protect my system against the phases. So I do the encoding, I apply the MHALLA Mehdi, I have the plus plus plus, and now I have a system that is robust to phases. And then I can compose and protect each of the qubits against the amplitudes. So I'm putting 9 qubits for 1 qubit of information. So how would I write it? You see that the system of 2 to the 9 by 2 to the 9 matrices can be viewed very simply in the direct notation because there is 3 blocks. 3 blocks of 3 qubits each. So if I write E plus 000 plus 111 over square root of 2 and E minus 000 minus 111 over square root of 2, if you read what happens here, you will see that the zero logical is taking 3 copies of E plus 3 copies of E minus, or 3 copies plus E plus minus 3 copies of E minus. So remember, instead of having 3 copies of 1 qubit, we have 3 copies of 3 qubits. And now what happens when we apply X on 1 qubit? But 1 qubit is 1 among the 9. So if we apply X to 1 qubit, you see in each part of the superposition, the system is a tensor product. So I can look point by point what happens. So if I apply X to the qubit, I don't know, this 2, X2 to E plus, I have, it becomes, instead of 000 plus 111, it will become 010 plus 101. Okay? It's just to get used with the notation, but it's not that complex. It's just I'm having 1, I'm encoding as 3, and at each time I just use direct notation. I'm saying this is what's implicit is tensor product. So this is tensor product, this is tensor product. Linearity is just everything like this. I can do sum, and when I apply somewhere, what means that I don't touch all the rest, so identity everywhere except where I point. I have 3 qubits here, 3 qubits here, 3 qubits here. When I apply, it flips. Okay, and what happens when I apply Z? When I apply Z to E plus, what does it happen? Do you remember what Z does? Z flips 1 with minus 1. So no matter which qubit of the 3 has the Z of E plus will become E minus. Whether you apply Z on the first, on the second, or on the third. Why? Because 1 tensor minus 1 tensor 1 is equal to minus 1 tensor 1 tensor 1 is equal to 1 tensor 1 tensor minus 1. The complex number goes through it's the C tensor product. So the same thing. Okay. But what happens if I have both error? Because what we have seen is I have to deal with identity, but that's easy to deal with identity, means that nothing happened. I have to deal with X error, and I have to deal with XZ error. So what happens if I happen to apply XZ? When I apply Z, I change the sign to minus. And when I apply X, I change the second one to be different from the others. So I can first look at bit flips, but bit flips is still detected. Because if I'm looking on the standard basis is which one is different from the other, the measure will give me always the result 2 with probability 1, and the state will be unchanged. So I can detect the bit flip, and I can correct the bit flip because I can apply X on the good one. And then I find myself with 0, 0, 0, minus 1, 1. So I can correct the bit flip by applying Z to any one of them. So I can, by looking at each block, look if one of the block has an X or an XZ, apply the correction, and then compare the blocks between themselves. Did I write this? No, I haven't. See here and let's see. Okay. So by looking at each of the qubits, each of the blocks, by measuring block by block, inside the first block, I look if one is different from the other. I can detect if X happened in the first block. Then on the second block, detect if one is different from the other. I can have X on the second block. On the third block, I do the same thing. And then I was able to detect X and to correct it. Even if it's X inside with this, then I have to check if there is a remaining Z. How do I check if there is a remaining Z? I just need to look at the block, to look at they measure an E plus or E plus minus T nodes. It's exactly the same thing. And I'm able to detect my phase error as I had before. So we corrected the X, we corrected the Z because Z of E plus was E minus. So if I measure with E plus E minus basis, I see that one of them was not the same. And I corrected the XZ. So basically I corrected all the errors. So I'm able with this circuit to encode 1 qubit into 9 qubits and to be resilient to errors that touched 1 qubit. Usually what we did classically, I told you it was the repetition code. You can generalize the repetition code to more general linear codes. So basically what we do is you consider coding the lines of the generating matrix and you use a parity check matrix to check if there is an error. So you say, I have this parity check matrix Hx equals 0, it means there is an error. I define a syndrome. And this is what is used in error correction to decode classical words. And we say that the code has parameter nk. If I put n bits, encoded k bits in a space of dimension n, n. The repetition code is just the simple one because I am encoding with the line 1110001. And the parity check matrix will be to check if first was like the second or second is like the third. If both are okay, then first and second are the same, second and third are the same, so I'm in the good subspace. So it's always the same problem, the same thing in classical. I'm using subspaces and I'm putting the information in the good subspace. And I'm saying that the error will not act on the amplitude. It will just move me from one subspace to another. So I just need a way to go back to the good subspace. And I don't care. I mean, my measurement will say either nothing happened, or okay, there is an X there, or Z error, X and Z, I move to the diagonal down subspace, X error, I moved here, I move here. So I decompose my spaces and just subspace. And in fact, we have techniques to translate codes classical codes to build efficient quantum codes, because here we had 9 codes, 9 qubits for 1 qubit. So you can say, how does it scale up? How can I do better for larger systems? And one proposition was how to use 2 linear codes to build a classical code by using cosets. I will not say the details here. An interesting point to see why this error correction scheme works is the stabilizer point of view. What's the stabilizer point of view? It says that if I take the state plus, x psi is equal to psi. It's the eigenvector of value 1 of x. But the eigenvector of value 1 of x is well defined. So if I know that I'm the eigenvector of value 1 of I, if I'm stabilized by x, I know what I am. And if I maintain my state is 0, so I can view it as the eigenvector of value 1 of z, because z has 2 eigenvectors, 1 minus 1, 1, 1. I go associate eigenvalues. So, and the key is that if I have commuting sets of Pauli operators, they will form a group. I'm looking by commuting, so it's an abelian group. And this is the way to describe a state or a subspace by fixed points. And the subspaces will be commutation or anti-commutation, but this is a way to describe the circle. What does it mean? It means that my psi 0, 0, I put it in a set such that Z2 psi is equal to psi, Z2, the global psi logical is equal to psi logical, and Z3 psi logical is equal to psi logical. So the subspace is the subspace of states that are stabilized by the group Z2, Z3, because Z2 and Z3 acts on different subspaces, which by definition, I don't know if you remember, mean that it's tensor identity, and the identity, of course, commutes with everything. So I can see it as the name of my subspace is the subspace stabilized by Z2, Z3. So I know all the operators that stabilize, and I have this information, that extra information that I put, that I will try to detect and correct to see if an X or a Z happen. And the set of operators that preserves this polyset is called the Clifford group, and it's a very important thing in quantum computing because it's the part of operation that you can simulate. There are other types of code where to shoot. Now, I told you this can be seen as stabilized by some states, but I can take the opposite point of view and start with looking to who is stabilized by what. So we can start to, from some topological reason, for example, the famous one with the surface code is the most used by physicists because it's the easiest to implement with many systems. Say, okay, I can view faces and vertices as conditions to define groups, and I can put X condition of commuter for stabilizing and Z condition of stabilizing, and defining my code from the surface. And in fact, it can be done from chain complices by saying, okay, these are my Z constants. This is the part that I want stabilized by Z. These are the part that I want stabilized by X. And I'm defining a code this way. So we can define a stabilizer by 2 binary matrices, and I will use it to encode quantum information by looking at subspaces. And what was built recently is low density parity check matrices. It means that we want codes that are easy to check. It means that I don't want stabilizer with large weight. So I want a group generated with low weight elements to describe my. So if I have one, I can do the surface code, I can do also the toric code. The idea is instead of taking the surface, I'm taking the torus and I'm connecting the border. And these are not the optimal codes in terms of capacity because I have square root of n qubits. I mean, I have one for, it's not, it doesn't have the good parameters for scaling, but it's the easiest to do, and it's the one that it was the first and the one that has been the most implemented in current technologies. It's exactly the same pattern, yeah.
Also for these codes, does this work quite nicely on all the different quantum computers, or are there like also architected by this then becomes
I think that all, no, maybe not in this sentence. Most of things are really compatible with set of structure because it's flexible and it's repetitive and it's simple. But sometimes sometimes they say, okay, I'm doing this, but I'm seeing time as one dimension and I'm doing this one, and this line is how it evolves in time. So some people present some strange interpretation or more, but I have heard about surface code in many different types, but again, I'm oblivious to the implementation because they're all asking for the same thing. So it's we have in the, for example, Qiskit or whatever thing will test what changes, and basically what changes is more the error model, the fidelity, the capacity to move gates, and the interconnectivity. The capacity to do the surface code will behave depending on these things. For example, and this why LDPC are nice, because I'm not asking for high degree. I'm asking for low interconnectivity. And low interconnectivity means not that much local reaction. So basically, physicists really liked it and made it a long, long time before it was studied for the quantum. I mean, it's not at all the one. Doesn't come from computer science. It might come more from physics, from what I think. But it's really the code that the surface code, especially with boundaries. So it's not the torus code, which is more like for us because it's more nice properties because you don't have to deal with boundary conditions. But it's the same with surface. You can deal with it. Like you have rotated surface code and things like this. But basically, it's very physicist friendly. So the idea is you have red and blue edges, horizontal and vertical edges. And you will say that, okay, I will connect faces to the edges and vertices to the edges. And I will define my stabilizer depending on the position of the qubits. So I say, my qubits are on the edges, and my family of constraints that has to be checked are either on the vertices or on the surface, or on the vertices. So I have to take, you remember that I have X and Z that we will have to check, because for the show code, as we have checked by hand, we built an X stabilizer and then we built something that is built on the other one. So basically what happens, you lose a little bit, but you can symmetrize. Okay, why you lose a little bit? Because the fact that you know that you have an X implies an incidence. So it's not the same as decoding the X only and then decoding the Z only, even if the error are, even if you have independent model. The fact that you know that you have an error is not the same. So if you want it to be completely optimal, you should do diamond-like or organize your collection, but you don't lose that much by doing independently X correction and Z correction, because now we are back to classical error codes. Because now we have just a binary matrix, we have an error that happens, I have a set of checks. So now I see my element as checks, and I have satisfied checks or unsatisfied checks, and I want to find my error. If I have an error, it means that one qubit has been flipped, then two checks will be unsatisfied. So instead of being in the commuting space, I will be in the anti-commuting space. It's just one bit of information that I have. It's just I'm playing with commute, anti-commute, with changing the sign. Okay, something to know that's specific is in fact that when I add a code word, you still in the code. I mean, I'm looking for errors that are not loops. I mean, the encoding things are things that goes around the circle. These are my logical cues. Small parts of the torus are redundancies that are in my substrate, that they don't make me change my commutation relation. Why? Because it satisfies all the checks. So adding a square doesn't change the satisfaction because I added 2 clicks on each of the symbols. So it's a 0 of the parity check. You remember the parity check was saying, okay, if my parity check is 0, that I'm in the code. If my parity check is 1, then I have to do something. And on the question of decoding is, okay, I detected that I have a problem, but now can I fix it? So if you detect something like this, it can be fixed by 2 paths. In classical code theory, this is a more probabilistic, a more unlikely case. I mean, you can see I have a phenomenon, I have an observation, and I'm looking for the most likely explanation. That's what you do all the time. Because I'm doing subspaces, I'm saying, okay, I put some space, all right, my words, now I have spheres of resilience. I'm saying if there is noise, I didn't go too far, or I went too far in the way I want to, so I can come back and go, okay, now I'm able to correct, and the distance of the code will be, how can I isolate them? How can I put spheres that put words far apart so that error doesn't put them change to one to another? The specificity here is that you don't really decode the error in quantum. You decode the class of error. Because you don't care, the state is the one, by definition, I'm using a space as a state. As I told you, my state is the one stabilized by ZZ, for example. So if I add a Z on 1 or a Z on 2, it still be the state stabilized on ZZ. So these two errors will be equivalent quantum. So quantum decoding is more subtle because you don't need to look for the actual error. You need to look for the more likely class of error, which is not the same computation as in the what we do classically. Okay. So that's it for this first part, what we did physics, problems of error, and an overview of error correction. Other questions? No? Okay, so let's begin to the right.
That again, +3. Yeah.
Okay. Okay. So before what we have seen until now was that we have seen what is quantum information and quantum computation, how to do things, what physical system corresponds to. That we have error that we can correct, that we probably can do more stuff, more things than that we can do classically, but not for all the problem, and not as simply as just by superposition. Before going back to implementation, for example, to show you that how to program and to go further with correlation, one other aspect that is very fascinating is that sometimes quantum help us understand classical. It might be very surprising because it's adding things that seems applicable only for small things. But in terms, you remember we discussed complexity, we discussed complexity classes, and we said that complexity is a bad theory and we cannot separate things with the tools that we have. But if we look in terms of languages and what's above, one very powerful tool to understand was the notion of interactive protocols. What are interactive protocols? If you suppose that I have an all-powerful friend that I'm discussing with it, can I recognize words? Can I recognize languages? And a celebrated classical result was, yes, this interactive protocol makes sense. They recover exactly all the problems that I can solve with polynomial space. So if I had infinite time, any undying man with a polynomial space and infinite time can do exactly what he could do with interacting with a prover that has no limits in computation. What happens if you have many provers that doesn't communicate? Proof. And here, at the opposite of the classes for which we can say nothing, these are separated classes. We arrive to non-deterministic exponential sets. We can have higher classes with many provers. If I not only I have one all-powerful friend, but two powerful friends, and I forbid them from communicating, I can recognize a wider class of languages. And decidable languages, you remember we had Turing machines, and I want the problem to have to say if the word is in the language or if it is not in the languages. One very important result 3 years ago, or something like this, was very important, is that RE is equal to MIP star. What does it mean? It means that what makes sense, I'm supposing that I'm having very powerful provers and discussing them and trying to recognize the language. If I don't forbid them from sharing quantum resources, so they are powerful, they have all power of computation, I forbid them from communicating, but I cannot know if they share quantum sets. And here we reach exactly the class RE, which are, I can decide, but only in one direction. Another part with commuting algebra and more complex tools, but it's related to quantum, characterize query. And if I look to the problem that I can find quantumly with zero error, it's again a quantum class. So the classes of complexity of languages, if I think in terms of processes, they are clearly and neatly characterized with entanglement assist. So instead of saying they don't communicate, is relaxing, they don't communicate, but they can share entanglements. One tool that's for this thing that is very nice and very important is that somehow you change the rule of the thing. You say, okay, I have a game that I want to decide, and I want for my instance to decide if it's in the language or not in the language. And basically what's crucial is amplifying the difference between the soundness and the completeness. So if I know that my winning probability is either high enough or low enough, I will be able to amplify it quantumly, and the techniques are, but it's very interesting to see from the conceptual point of view that quantum allows to characterize things that look completely classical. Okay, if you come back to Earth and what we can do in practice, I promise that I will show you Qiskit. So we discussed it when we did algorithms that there were implementation of algorithms. There are ways to program with high-level languages, and Qiskit is one such tool. The idea is if you want to apply quantum circuits, to construct circuits, to test the state that you have, you can use Qiskit, And you can even use it because they have backends for different models with models of error for implementation and different techniques. It's very friendly. I mean, I discovered it when I was preparing the lectures, and it's just you read the tutorial and you install. It's Python. You import packages. Here you import quantum circuit, the simulator, how to draw a circuit, how to plot histogram, and you import stuff. And then the syntax is quite natural. So when you say QC is quantum circuit of 3, means I want to create a quantum circuit that has 3 qubits, and I will use 3 qubits to other results. And then you say I apply a Hadamard to each qubit. It draws this thing. So I have qubit 0, qubit 1, qubit 2. I applied Hadamard to this thing, and I have this. And I have applied Control Z to 0, 1, Control Z to 1, 2. It just applies Control Z, and it gives you the circuit that you obtain by doing this. The?
How do we make it bigger?
No. I'm sorry, I will. You know the interface of this thing. Yeah, sorry, I don't know. I will not stop just too much. Yeah, I mean, it's not very important. It's just the circuit, the drawing is here, and the command is. Yeah, I mean, you don't need to learn them. You will type them and you will see them. That's the tutorials. That's to have an idea about what does it look like. I mean, basically, I can ask it what is the state vector, and it will give me complex number with coefficient. So it puts 0.35, 35 something. And basically, it wants to say it's uniform, and the side has plus, minus. I mean, it's described the states. It says this is the coefficient of the odd 0. You remember it's a 3 qubit state, so I have 8 components. So they put the complex number in front. So if I put QC measure 0, 1, 2 in 0, 1, 2, it means I measure the qubit, each qubit in the correspondence classical bit, and it draws this circuit, means that it draws this, and then it measures. Then what you can do is run a simulation. Okay. Run a simulation is that you say, okay, now this circuit, try it many times. The number of shots is 1024, and draw a histogram. And what he draws is, okay, this is the count, this is the number of time I got 0, 0, 0, this is the number of time. And basically it's just really classically simulating what was proposed. There is a physical mode that access to a real implementation, and the advantage is that it could allow you to access to a real hardware to test the property of a real hardware to, for example, to characterize the errors, to see things that it could be connected. It's done in a modular way such that it can interface different types of directions. But you can use it for them just with simulation. And then what you see. So basically what you see here is more or less they are the same. So it's I'm playing physicist. Okay, it's a uniform product. So it means that for any n, if you reproduce this, we will have a uniform superposition. Physicists would say. Okay. Then what happens if you change the circuit? If I add the Hadamard on 0, now I will have another structure. So what I'm saying is that if I apply 3 Hadamard and then Control C, if I measure, I have everything. If I apply Hadamard there, something will happen. Okay, something to say that something will happen. I tell him, okay, run the simulator, transpile, whatever, and simulate the run and count the result. And what happens? Oh, we have only 4 results. So if instead of measuring, I apply 1 Hadamard, something happens. instead of having everything, I have only half of the space. And what half of the space? 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0. So it's the even subspace of the amplitudes. So what happens if instead of doing one hadamat, I do 3 hadamat? If I do 3 hadamats, it's doing something similar, but it's the odd subspace. So you see that if I do the circuit with 3 hadamat and 3 control C, if I apply hadamat everywhere, I will have only the odd subspace. If I apply hadamat on one place, I will obtain only the even subspace. Okay, I showed you that it was on the first. By to your mathematician, you see that there is a symmetry by permuting the lines. So you know already that you will also have the even subspace when you measure only the second and third one. Okay. Hadamard, you have the even subspace. Other, you have the odd subspace. Okay. If you measure in the beginning, it's like, okay, you started with 0. You have a big histogram. Okay, so there are languages that allows you, if you don't know, I mean, if you want to see it like this, how to visualize the action of the circuit graphically. Let's go back to trying to understand this. Thanks. Okay. What were you seeing before? Let's try to understand what's the property that we were seeing. In fact, quantum information allows to create a new type of correlation that are called pseudo-telepathy. It's because people from outside the quantum world, people who doesn't know that the quantum exists, people who are used to start from marginals and to define, to extrapolate on things, would say it's not possible they are pseudo-telepathic. It's the same argument of Einstein about Bell inequality, but pushed to the extreme where I'm going to the deterministic setting instead of saying, okay, the expectation should be below some value. It's not a purely quantum phenomena because on the there I will explain after the word, it's called contextuality. It means that if you look locally, the picture has a global meaning, have a local meaning. If you look locally there, the picture have a local meaning. You see that people are going up and going up and going up and going up and going up, going up. Globally, I've lost the meaning. But there is no continuous loss of the meaning. I mean, any part of the circle that doesn't capture everything, as long as I'm losing someone, it completely makes sense. This part is the part that is going up. But all the parts claims to be going up. So what's happening? So local consistency, even continuous local consistency, doesn't guarantee global consistency. In mathematical term, it means that if you have a breadsheet, you are not guaranteed to have a section, a global section. But let's go back to the game and to see why quantum is in this type of phenomenon. So you take 3 players, so 3 classical players, and the 3 player will be presented a ball that is either blue or red. So each player will have 1 bit of information. You allow all the players to do one action, that is one bit, so either to take the ball or to let the ball to the one who presented to them. Okay. And you will define a game in which each person has a local view of the situation, which is the situation every day, because everybody has to take action depending on what he knows, and which behavior doesn't depend only on the local action, it depends on the global action. So I want things to work well, but I'm only able to see parts of what I can act on. So every player is presented a ball that is either red or blue, and there is losing configuration that they want to avoid. They lose a lot if some global configuration occurs. What are the forbidden global configuration? They are, if the presented set is all red, it means if the three players are presented red balls, and the set of balls given back is even, then they lose the game. They want at all costs to avoid, when being presented 3 red balls, to give back an even number of balls. Remember, each player will see only its ball. He will have a decision to make depending on what he sees, but of course, before they can coordinate as they want. The second set of losing configuration is when they are presented exactly 1 red ball and 2 blue balls. And in this case, they lose if they give back an odd number of balls. I mean, given the colors, odd there means either 1 blue, 1 red, or 1 red and 2 blue. And even here means even nothing or 2 red. So the game rules are very simple. There are configurations that are global, that they want globally to avoid, but each person will take a local action depending on local knowledge. And to ensure that they cannot communicate, I can do like the Bell experiment. I can put them in different places very far away, have the reviewers look at their watches, or the PhD students look at their watches, and they synchronize with the atomic watch when they will ask the question, and they will ask the question exactly at the same time, and the others are supposed to answer immediately. Okay, so for now, I'm just defining a combinatorial game, a multipartite game. So let's recall the setting. 2 families of presented sets are crucial, otherwise they win all the time. They have no condition. Of course, they could have they don't know. I mean, maybe they present to them 3 blue balls or 1 blue balls. In that case, there will be no losing condition. They are not allowed to communicate. The experimental is give a ball to each one. So here it was type root, type blue, type red, type blue. They have local action, keep, give back. I look at the global set of balls that are given back. It is on the losing set. So this is an experiment run that can be done. That's completely classically defined. There is no quantum here. I'm saying this is the rule. This is what you have to do. Okay. Why it's called telepathy? It's because classical people will be able to quote unquote prove that it is impossible. Why? I mean, for each player, classically, if I can answer the problem perfectly when I have a blue ball, and I can answer the problem perfectly when I have the red ball, then I have a function that allows me to answer whether I have a blue ball or a red ball. So I can add counterfactuals at the same level and with no problem, because if I can answer this situation, my strategy that I'm applying when I have a red ball and my strategy that I'm applying that it's a blue ball are strictly separated by the questions. So can be defined at the same time. So what are the possible strategies? You remember I have 1 bit of input, 1 bit of output. So there are 4 0, 1 to 0, 1 functions. The constant 0, which means I give back 0 ball, so it's always keep. The constant 1, which means I give back 1 ball, so it's always give back. The identity, so it's keep if and only if it's blue. And the nut, which keep if and only if it's red. So if I say that the type of the player of the question is 0 if it's red and it's 1 if it's blue, I can associate to each player the number of balls he gives back when his type is TJ. So AI of TJ is the number of balls the player I gives back when the question is of type TJ. Okay? The global behavior can be explained classically with correlated behaviors of product of local behaviors. But then, if I take any product of answer strategy, any product of local behaviors that might happen, if the player 1 uses the strategy A1, the player 2 uses the strategy A2, and the player 3 uses the strategy A3, each one takes his decision depending only on his input. So if this strategy could be taken with some probability, and the players never lose, it means that all the time, A1 of 1, A2 of 1, and A3 of 1, if I apply the 3 of them, the sum of the ball should be even. And at the same time, when I apply A1 of 1, A2 of 0, and A3 of 1, the sum of them should be even. Because this configuration is a critical configuration. If I apply A1 of 0, A2 of 1, A3 of 1, it should be even. And if I apply A1 of 0, A2 of 0, A3 of 0, it should be even. And here you see that it's impossible. So any behavior, any explanation as product of local functions that could be taken with some probability induces a probability of losing because the question could be on either. So this game cannot be won perfectly if people don't believe in quantum. And in fact, graph states are states, you remember we have discussed the stabilizer that characterizes the state that was a group of Pauli. One particular state that's defined as the graph state is the one that is stabilized by something that looks really like the adjacency matrix of the graph. If I put X on the identity and Z where I have edges, I will obtain a group of Pauli elements that commutes. So it will correspond to what we said before about the stabilizer. It means I have n independent ones, so I will fix exactly one state. So there exists exactly one state that is stabilized by the group generated by these 3 Pauli operators. And one way to view measurements is to put the measurement in the middle. It's okay. I mean, for now we have done with projective measurement with putting P here, but the norm of P psi is equal to psi P dagger, which is equal to P psi, which is equal to this quantity. And in fact, when I look to the Z is the symmetry. So I plus Z over 2 is the projector. And I minus Z will be the complementary projector because the sum of them is identity. So the 2 projectors that can be associated to the symmetry Z can be described like this. And quantum physics says that if Z psi is equal to psi, Z psi, this is equal to psi, then x is not psi, but it's minus 2. Why? Because zx is equal to minus xc. Basically, what I'm saying is that quantumly, if the players apply this strategy, they will do a behavior that depends on the color of the ball that is present. In the setting, I never said that they should be unable to answer whether the ball was blue or red at the same time. I say that they should be answer whether the ball was red or blue. So if the ball is red, they can answer. If the ball is blue, they can answer. But quantumly, that doesn't imply that they can answer at the same time if it was blue. Because it could not. It's either blue or red in the setting. And this is why quantum will be able to do what's not possible classically. I mean, one way to see it is to see events as points. So let's look, for example, Amy, and say, what is the possible question that you could have? You could have the type 1 or the type 0. Type 1 is the blue hyperedge, and type 0 is the red hyperedge. So there are 4 possible events that are, I got 1, I input 0, I got 0, I output 0, I got 1, I output 1, and I got 0 and output 1. So what does it mean, a deterministic strategy? A deterministic strategy means picking a function. Okay, what's the function? It's a sequence of 2 constructors. I mean, I need to answer when I have 1 and to answer when I have 0. If I group these 2 together, I have the constant 0 because I always say 0. If I have these 2 together, then I have the identity. Then I have 1, or I have the nuts with viewing it as the circle. So constant 0, applying constant 0 with some probability will induce the possibility of happening of 2 events with some probability, depending on the question. The first is when I apply constant 0 and the type that is asked is 1. The second is when I apply constant 0 and the type that is asked is 0. Identity, if I apply the strategy identity, these vertices might happen. Yeah, now you look at the vertices as possible configuration that corresponds to an instance of the game. Yeah, I forgot about the second one. I'm looking only at one player, which will presented 1 bit and which will output 1 bit. So each explicit configuration or run of the experiment is one of the vertices, and each decision-making process or each behavior will create possible happening situation for 2 events. Okay? So what happens when we compose experiments? So now, instead of having any that has 1 type asked, 1 type that she gives, we have 2 players. Each player will have 1 type asked and 1 answer. So basically, if we compose, we take the product structure, and we see that we can group the events with saying, okay, here I took this one, so 0 given 0 from the first. So she had this type 0 and she answered 0. And here he also had. Note that I'm using 2 representations of the same thing. I'm using A maps to B for doing B knowing A. So the bar means I'm answering 0 knowing that I got 0. And the arrow means I start, it's reverse. One is conditional probability. The other is what's the question implies what's the answer. Is it okay? Well, there are questions about the representation. Basically, I'm saying I have two players, a situation, an event. I want to represent it by a vertex. Each vertex, I take it back and I take it down. It has an x coordinate and a y coordinate. So each vertex corresponds to an event, and each event has a sub-event for player one and a sub-event for player two. An event contains two parts. What was I asked? What did I answer? So what was I asked was, did I answer at the level of Amy is drawn here. One gives one, or equivalently, one for player one, given that it has one for player one. Events for Jack is given here, and common events is here, which corresponds to the product. I take this, and this is the situation. I'm just trying to represent what could happen. You remember when we did the physics part, what he was saying that, okay, I'm doing the experiment that I'm counting and I'm adding. So at each time I'm doing an event, I will have a +1 to one of these configurations, which means that this occurred one time, this occurred one time, this occurred one time. And the counting method will generate a description of a run of the experiment. Okay? So at any time, my run of the experiment is a bunch of numbers to say this situation occurred 5 times, this situation occurred 2 times, this situation was 5 times. Is it okay? There is something that, I had 3 players, now I'm doing one by one. So I started by 1 and then I'm taking the second. So but it's just the same, it's just to explain how I'm building the events. Okay. Sum of 2 digits. Okay. What is an event? What does it mean if I look to the sum of events on the red colors? It means exactly all the events for which the type 2 was 0. All the events for which the type 2 are 0, there are 8 of them. And they are these ones. The split here is whether Amy kept the ball or gave back the ball. 0, I remember the number is the number of ball given back. So 0, she got the ball, she gave back the ball. The ball is red, that's what 0. So each events can be grouped onto larger events. And if I look at 2 disjoint lines, this is a fixed type for Jack. Okay. What's the non-communication constraint? Because now if I'm looking to events, I want, in my setting, I said I'm looking only to things with non-communication constraints. In fact, the non-communication constraints will forbid us of some configuration. Why? Suppose that these 2 events never happen. These 2 events never happen. How do I read them? At each time Amy keeps the red ball, Jack is never presented a red ball. So it looks like a set of events that mean that the experiment is not run correctly. It's as if when Jack is presented a red ball, he transmits information to Amy. So we don't want this type of element. So what we don't want we don't want both disjoints to be empty, because if I have two vertices like this that never happen, so for which the count is 0, it means that I have a causal inequality. I have a communication. I have a suspicion of communication, because there is a correlation between the ball presented to Jack and the answer of Amy, knowing that she is presented the red ball. See, what I'm saying here is, if this 2 is equal to 0, I can send this equation to a sentence that says, at each time, what do they select over? At each time Jack is presented a red ball, if Amy is presented a red ball, she doesn't hit. So this is a logical sentence. And this logical sentence relates the behavior of Amy to the behavior to the type presented to Jack. So it contains, when you measure information with all the known measure, it will contain the violation about the non-communication principle. But here I'm trying to view it in a very combinatorial way. I'm looking, I haven't yet defined probability or whatsoever. I'm saying this is already should be problematic in the terms of information, if I could define information in a combinatorial way. There is no nice definition of information without probabilities. So let's go back to what's really formulated to explain is just, let's put a probability model. To say that deterministic is just 1, 0, probabilistic is any number between 0 and 1, and I want the sum of probability to be 1. So what does it mean? It's the model in the study of contextuality. It means that it's a frequentist model. I mean, it's just number of runs are changed to probability. I normalize. I say, okay, 30, 30, 60 is just, all I need to know is just, it's 1/2, it's 1, 0. And then I will not play with numbers, I will play with probabilities. And I will say, okay, this is a probability distribution that represents the experiment. Okay, so what's a deterministic behavior? Deterministic behavior is exactly a behavior when she has 0 and a behavior when she has 1. So deterministic means I repeat all the time the same. So either when she has 0 she keeps, or when she has 0 she sets. So I will forbid 1 point. And what is a probabilistic behavior? It's a probability distribution over the deterministic behavior. So probabilistically, what you can use is with probability 1/2 strategy 0, with probability 1/2 strategy either. So instead of mapping the vertices that are the global events to 0, 1, to say this could happen with some non-zero probability, or this could not happen, we can have even classical probabilistic behavior with probabilistic mixture of deterministic behavior, and we can have quantum behavior, because we can say, okay, the probability that she uses is obtained by some quantum measurement over some quantum sets. And we can even have stronger type of behavior, is saying that the only restriction in the context is the general contextual rule. It means I don't want to be able to make sentences that start with when player X have type Z, then player X prime different than X do something with different margins. I don't want the behavior of one player, even when restricted to a specific case, to depend on the input of the other. So I will put them like this for a reason that you will see immediately. is that, yes,
We have an example of actual probabilistic behavior that is not.
yes, I will show you just after. I mean, what I told you, I mean, to have deterministic behavior, it doesn't happen for 2 players. It happens only for 3 players. The smallest example where I have probability 0, I needed to have the 3rd player, and I will show you the representation. And as I was interested in the 0 case, which is the top, because it's the one that didn't discriminate between yes and no, between RE and co-RE, I needed to go to the 3-player game. But now to explain, if I'm explaining on probability of success, I can restrict myself to 2 and the Pell experiment. And so that I'm explaining how I combine classical strategy and how combination of classical strategy will become phases here. Because when I'm saying he applies the identity, I'm saying that all this can happen with non-zero probability. When I'm saying that she's applying the identity, she's saying that all this can happen with non-zero probability. So the events that are touched by the pair of strategy, identity times identity, are these 4 points, which corresponds to the definition of identity. They got 0, 0, they answered 0, 0. They get 1, 0, they answered 1, 0. They get 1, 1, they answered 1, 1. They get 0, 1, they answered 0, 1. I'm saying that by doing this projection, I can represent the classical strategy as the faces of my drawing. And the events, if they apply this strategy with probability P, it will induces with some probability this thing, this way. This thing. Okay. It's a bit more complicated than that, but not that much to define the events. In fact, the events for the contextuality scenario, as defined in the paper that I cited with Assin, Fritz, Annabelle Nonsens, and De Verrier, say that, okay, in fact, the events I can associate to each vertex from one side, an edge on one side, and I can change midway. What does it mean? And this is what they call a context. So the context, when we have one player, the context was, what do you know? What was the question that you had? What is the context when you have 2 players? You have to take one vertex from one side and one edge from the other side. So the context, T1 equals 0, T2 equals 0, corresponds to 4 sub-events. The context, T1 is equal to 1, T2 is equal to A1. What does it mean, this one? It means that the type of the second is equal to the answer of the first. It's another valid context. It's obtained. How does it obtain? It means that I'm looking to this edge, and for this vertex, I take the one edge below, and for this vertex, I take the edge above. So from one side, you take, for each vertex, you associate an edge, and you say this is a hyper edge that is a context. You can also have this form of context that are T2 is equal to 1 and T1 is equal to A2. Mean that I fix T2 is equal to 1. So I will never go in the red edges. Jack will always be presented with blue ball. And depending on the answer of 2, I have the answer to the type of 4. So these are events that make sense. So there are events that are consistent with the fact that the measures are independent. There is contexts that are independent with Jack measure is related to Ami's outcome, and the other one, Ami's measure is related to Jack outcome. Okay, remember, I mean, they measure and they output the result of the measurement. So the A is the result of the measurement. So what is the non-signaling as defined by this type of Wood probabilities? It becomes just a linear equality. It says, for any line, I don't want the probability of this one plus this one is equal to probability from this one and this one. So you recover the combinatorial characterization above by saying, okay, if I have these two is equal to 0, I will have these two is equal to 0. I will need to connect them. Because probability will still be positive number. That's simple. So they say that vertical Lorentz equalities are equivalent to sum to 1 for fully rounded functions. The rule that we have seen before, that these strange contexts that are built by taking edges and hyper edges in the strange way and looking at all the possibilities, saying that the probability for all hyper edges sum to 1, it means that I cannot exclude from the probabilities defined with the setting any possibility of communication in one direction, are the same as saying that these simple equalities. So what happens quantumly? Quantumly, they share states, and depending on the outcome, the answer is the norm when measuring with a projector. So when they have 1, he measures with plus minus. When he has 0, he measures with 0, 1. And we do similarly here. So what can I read in the event? In the event, I will read a tensor product of projectors. Each event will correspond to a choice of projector from each side. And remember that they can choose their projector because they know the ball they see. So they can act locally on their shared common state. So quantumly, we can produce probability distribution that are not consistent with the notion of the existence of that we are in the convex sum of the products of local strategy, even when correlated. This is exactly seeing here, if you remember the slide for the Bell inequality with the integral of the probability over omega, the products of things, is exactly the same thing. That we go beyond the Bell inequality, but we go beyond it. How far we can go beyond it? What I proposed below was a combinatorial characterization. So it was, if I respect that I give you a probability distribution that never have 0 on these things, it respects the condition. What does it mean? It will not have a hole like this. Or in terms of probability, if you have already the probability distribution, I can put 1/2 everywhere, and they will have always sum to 1, and the sums here will be satisfied. So I'm violating no communication rule. So defining reality by non-violating communication rules is here what's called the CSSH game or the PR box. This is a game that is exactly the one we have for the winning probability for the Bell inequalities. It is strictly more in quantum than in classical. What is the maximal probability of winning to this game classically? Suppose that your distribution is even. I mean, suppose that all the questions 0 and 1 are asked with probability 1/2 for Alice and for Jack. What is the best probability of winning classically? Can you tell me? What are the classical strategies? The first, the side, this one, the squares. So what is the probability of losing if they choose a square? That's the probability of picking the bad one. So the best strategies have 1/4, so we have 3/4 to win. The best strategy loses in 1/4 of the cases, because any product of classical strategy has at least one forbidden point among the 4 possible ones. So any convex mixture will stay below this rate, and any classical behavior will stay below the 3/4 rate. And the quantum best solution will still not be perfect, but it will win with more probability. But when will it be perfect? The game that I told you is the same. I'm adding one more player, but it's this exactly the same construction. Just open your mind and take the thing. I take this, I add one direction, I repeat the same pattern with adding one direction. And I'm saying now, I have another player, this is Charlie. And when he does 0, we are here. When he does 1, we are here. When he does identity, we are here. When he has identity, here. So instead of having surfaces, I have cubes. But classical strategies involves each 8 points. And the condition that I told you were exactly this sweeping diagonal, but taking only half of it and lifting it to make it half on a layer, half on another layer. Instead of having the two diagonals at the same time, I created a scenario where if I project, if I look at 2 times, I will have exactly this diagonal and the diagonal afterwards. But in fact, it's moving so that I don't have this problem. It still blocks the classical strategies. Why? Because no cube avoids everything. Because if I take this cube, I will have a violation here. Best winning strategy, 7, 8. This one has 4, and this one has 1. So I will not be able to win better than 7, 8. For any product of 3 strategy, I have at least 1 forbidden point. You take this one and this one. Okay, of course it's a torus. I mean, so when I go from here, you can. So the best classical strategy wins with 7, 8. So if I say Alice has a behavior, Bob has a behavior, Charlie has a behavior, then they cannot win with more than 7, 8. But I told you that quantumly, they won perfectly. And even the experiment is reaching the fidelity. So there is no limit. It's not perfect, but it's as good as. So quantum saying that the proof is false, that you cannot say people act on what they say. You have an error in floated arrangement in the beginning by assuming the existence of a behavior of Charlie, depending on what he sees, unless you have a way to forbid sharing entanglement. So if you imagine a world in which entanglement exists, you have to admit it in the set of possible strategies. You cannot say, I define Charlie, I will present him 0, he does this, I present him 1, he does this, therefore I can define the function 0 map this, 1 map this. I mean, the luxury of the mathematician that has the freedom to define what he wants, when confronted to the reality of the physicist, where, okay, now do it and show me, I had to add the definition of possibility of entanglement. I cannot say everything will behave this way because I can look at this and look at this, the marginal are independent. So by definition of independence, it works, it doesn't depend. Something I didn't tell you. For any question, the behavior of any player is a perfect random bit. So not only they are winning the game, but they are producing randomness. So in average, you take any player, you take any question, you have a perfect random bit no matter what you answer the others. So you marginalize however how you want. If I forget the other, it's just random bits and they are completely independent. The players of 1 is 1/2 of identity. The probability distribution, the description of the state of each of them is exactly that of randomness. But the correlation is deterministic and is beyond what one could imagine if you consider things classically. Oh yeah, one thing I worked at is how multipartite the state need to be produce this type of things. Because, I mean, if I imagine the PR box allows to win to this thing, but yes, I will. Yeah, what happens if you have more player? I mean, what I propose as, I mean, what I use a planar representation because I like visualize things because I want to have a local decision. So I want to represent the global setting with a local embedding. So basically, if I add a player, now I add columns, and then if she's here, and I'm moving a little bit my vertices to encode the global answer. But just what I want to say is that the representation can be scaled to represent events where direction represents players and where I will have behaviors that are outside of the scope of imagination if I look only at marginals and independent and classical independence. So I will have perfect handle bits that have hidden correlation that allows to do perfectly things that are probably impossible in the realms of function, depending on what they know. I mean, extensions go even further because there is also a work on quantum causality where people think, okay, but now what can I do if I apply the gates in superposition of order? So if instead of thinking my circuits by doing A then B, maybe I can do a superposition AB or BA. And then I have new framework to describe what could be done. That is very interesting because it puts the time inside. The way I say, I don't need to respect causality outside, inside. I only need to, the only thing that I'm supposed to is that from the outside of the black box, it respects the quantum probability, the Born rule. And it creates even more correlation that are even wider, that are less understood. But yeah, okay, there is a huge debate about implementability of this type of things. So I discussed the last part that was fascinating for me is the correlation. I mean, how do I need to define things? Just a brief summary and extra basic notion to go further. Yeah. States in general, pure quantum states are just vectors. They are defined up to a global phase, and the nice representation is with cos pi x an exponential phase for the second. So in fact, you need only two numbers between zeros and one. From state, you can define projectors. And the projectors have also a very nice representation that is how much x, how much xz, how much zi. So in fact, what you need is a sphere, but only with real numbers, with a squared plus b squared plus c squared is equal. With this parameter, you can define the projector. With this parameter, you can define the states. In fact, when I was saying what they could do, I could have probability distribution over states. So I could imagine that someone is not having a pure state, but running a dice and preparing a state depending on a classical outcome, or quantum is even worse. But in fact, if I have mixed states, they are characterized by just the mixture of what they could be. So if I take the sum of the projector expression here, I define a matrix that is a Hermitian that describe what we call a density operator. So we have a way to characterize what we can say by measurement of quantum states. And also, I mean, see, this is not the same as the probability distribution of a quantum state. So it's an equivalence class. But we know how Hermitian matrices characterize probability distribution of a state. Basically, in the representation, it means that you remember we have the block sphere. In fact, in the center was identity over 2, was the completely random bit. And if we lose information. We cannot be on the sphere, but you need a rescaling because with some probability, you move toward the center. So there are three types of matrices that happens in the quantum world: the Hermitian matrices, the unitary matrices, and the symmetries. And when you have two, you have the other. So if you are Hermitian and unitary, you are the symmetry. If you are for qubit, if you are a symmetry and you are unitary, you are Hermitian. It's somehow it's obvious. You can see it immediately by the space. It's a simple matrix. And the most general measurement, in fact, one thing that is very useful in these games is to compare the difference of probability to seeing 1 and to see 0. So you will try to separate the 0 and the 1 and to separate how far they are from just saying a random bit. And you also have a very nice characterization with just these Pauli matrices. So you have somehow a bias of how randomness you are introducing in your measurement. If you are not introducing measurement, then you are a projective measurement. And if you don't put B, then you have even a rotation in the XZ plane. In general, people sometimes use qubits instead of qubits. What does it mean, a qubit? It means I have D possible state, and I would say in C to the D. But in fact, you can always, by doing one qubit measurement, view state as phase. Means that you can always do one qubit measurement on a qubit and view states as qubit, but just with phases that are roots of your unity. And very recently, it was shown that we know how to decide what is the state if I have many copies of it. And the secret is to do adaptative measurements. Meaning that if I have many copies of the states, and I have a classical description of a hypothesis, by doing adaptative single qubit measurement and the algorithm that I proved that is very simple, is just run and then condition your tree definition on what you observed, we can accept and reject with high probability if the states verify a hypothesis. So, and this is, yes, it's June this year. That means that even for simple properties of how, if someone prepares a state, I can distinguish it, things are moving a lot in the community and understanding is improving and improving a lot, even for the theoretical point of view. If you want to complete completely the picture, if you speak with people from quantum theory, they will not only speak about qubits, you will hear them speak about bosons and fermions. And these type of things live in infinite dimensional spaces often. Somehow, there are other things that live either on the symmetric space or on the anti-symmetric space. The bosons are like carrier of information. So they have modes. You pack them together and you don't know which is what, but you just know the number of bosons that you have is just what mode you are. And the fermions are the opposite. They are very individualistic. They occupy the modes, but they don't support sharing a mode together. So each one occupy a mode by itself. So they are distinguished one by one. There's a lot of the theory. They use operator algebra or sister algebra to describe how things work. Yeah, something that I haven't said, but that is very important. Yeah. Okay, I don't know if you remember. I told you that when you take the projector of the one and the projector of the other, the quantum result that I define is the tensor project of the action of the first and the action of the other for the game. I said Alice measure with 0 if she has blue and 1 if she has red. Bob measure with 0 if he has blue, 1 if he has red. So they measure with P0 tensor P1. And a huge debate on the community was we don't know this fact of the tensor product. So can we relax it to commutativity? So can I say, I mean, the traditional belief, the traditional quantum theory says that locality is by tensor product. And I could imagine increasing the dimension and going to the infinite dimension. The mathematical operator algebra framework likes commutative stuff. So they say if it commutes and the order doesn't matter, I would like to say that it's local. And people believed that it was the same. People believed that if the Hilbert spaces are big enough, then it will be the same as locality by tensor product and locality based commuting. And it was proven recently that it's not the case. That it's a strict separation, and this also is very nice because it's really said it's not the same. The dual thing, the algebraic things, consider duality as commutativity. The set of quantum correlation is not even closed. It's really a different type of object. So you have what happens when you go to infinite dimension, what happens in finite dimension, and what happens in the commuting. And these three sets of correlations defines properties with a strict separation. So you can reach more correlation if you allow just commute things for anything that commutes. Then if you allow, you don't restrict the dimension of the Hilbert space, and that's for finite. And one fun fact, and one interesting also very recent result, is that in fact, I don't need to think that there is something that is perfect and I start from it. Starting, if you have a norm, any approximate sister algebra can be turned to a perfect one. And I even know if you restrict the dimension how far I am from things. So we are understanding more and more the limitation and how we eliminate the noise to define perfect object from perfect one. And it works quite well. Okay. And for this part, the next part is more about projects, proposition of things that are interesting in quantum, and the part about my personal project. So let's take a break. Yeah, 20 minutes, okay.
Or we can stop with them. So now you need to share your screen, I think.
I couldn't speak. Ah. So, no. Okay. Yeah, I don't know what's happening.
Thinking about something.
It's still thinking. They close and open or?
Maybe. But it's still there now.
It doesn't stop thinking. Ah. You know what to do for Mac to. They start now. Hmm? It's confusing. You take this, but it refuses to switch between apps. Okay, we'll stop. Max, they are not supposed to. They are not supposed to
It's still going, no?
stop thinking. Try to force the boot because it's the book. Ah, no, I got my mistake. No, it's no longer answer. Ah, let's quit, but it don't have mouse. You know, let's quit. Ah,
It's bombing again.
yes, it's peanut. Gave up. Okay, I share again. And yeah. Oh. So let's continue. So what I want, just to share my point of view about what I found important when I learned from quantum information is that for me observation is a point of view. So different observation leads to different behavior, and it changes the state by default, and not all the observations are compatible. We have to admit then, instead of it is when I see in this way, it is. This should be kept in mind. It's dependent on the way you are looking at things. And the ontology of things does not depend to be the same. I mean, things that I can see, what I can see, I can imagine what they can be. All what I'm required is to maintain the compatibility of how they behave, how I act on them. Has to be consistent on what I can see from them. One other thing that is fascinating, that's everything that I knew had a reversible big picture. So I don't need to forget to understand. Basically, any density matrix, any observation, you can imagine that it's part of a large quantum system, and I have access to part of it. And accessing part of something big creates probability. The same as observing creating probability. So there are two sources of probability. My choice of action by measuring, and my possibility of action of having access to part of a system. Superposing allows to avoid to have to choose. So we can delay the choosing to the last part and unify, purify, and compose with imaginary objects, which means that I don't need, when I'm describing not the answer I have to give, when I have no decision taking that is needed, there is no reason to insert extra noise by adding probabilities. It's much more simpler and much more correspondence to what happens to imagine that everything is reversible until I have to act on it, or until my action on it depends on my knowledge of it. So there is two sources, and otherwise it can. Okay, for the ones that want to advance further and to learn things that are linked to what you look at and that are important results for the community, I recommend one of these 5 articles, for example, and we can, if you go read it as a group and you want to discuss it, I would be glad to see a presentation or to discuss with you. For example, there is a very recent paper of that group. Order is in QCMA. It means that a classical certificate is enough. I don't need a quantum certificate. There is another part that's click homology is QMA hard, so it's about the quantum difficulty of the problem in a setting. There is one that says that, in fact, when I want to change, to decompose things, I can see with positive object and co-positive object, and they link the graph characterization to the maps. So they link how to make an operator out of something that I can use. And it's interesting, the positive and extendability shows this phenomena that appears in quantum about extendability, in fact. But the fact that when the system has to work for bigger one. And the last one is a unified framework for quantum embedding. It's interesting because it's really close to topological stuff, to homology stuff. Not codes, okay. And the last is graph for stabilizer. It is Shore, the last is by Shore, and it's recent. It's very nice because it allows to characterize what are the states for which information can be preserved. Because if it's stabilizers, it means that I can encode classical information and manipulate them and correct it. Because I don't need to consider complex computing with things that I cannot recover. I'm interested only on things on which I could put classical information from a classical problem to answer. I give you links to more general resources. And then I want to speak to you more about and completely extrapolated things. It's a drafty, it's some thoughts that are, it's a personal view, it's a project that goes beyond quantum. And the idea is, can we get inspired by quantum to think more generally? You have seen that quantum says the position of the electron is not fixed. You have to think of it as a superposition of what can be and what can't be. Can we reproduce this and try to understand understanding? Why I believe that everybody shouldn't do math, everybody should do math. Is it a contradiction? No, because the first do, I mean, repeat, apply, do what you are told. And the second do means do from yourself. So it's rebuild, reimagine, and reconstruct the roots of math. And by the way, for me, SH or C are equivalent. It means that you can see equivalently that they could do math. It's a way to see it. Okay, it's a speculative work in progress. So, for example, when we heard what we heard yesterday morning, of course, we are always testing something. The question is, can I question this? Can I start from the fact of questioning? Do I really need to build axioms to do reasoning, or can I do things that will be adaptive by construction? Can I just try to make the meaning and build the meaning as a constructive process? So the questioning, okay, in the morning, another point is the citation is what's fantastic about this project of Fermat theorem, it's one of the guys who was proposing lean building of Fermat theorem, is that you don't need to understand the whole thing, you need to do your part. And sometimes it's useful to improve communication. But I feel that sometimes it's dangerous to look only locally at the local picture and to have people do things without trying to understand the global picture. Because fundamentally, we are humans, we are taking actions, and ethics is part of our behavior, and we should not lose focus that we are doing as students think that could be used for other stuff. And it is your responsibility. So you could not say, I'm doing this, I don't need to think outside what it could be used for, or outside what it is. It's important that people try to understand and they try to question the way things are defined. Okay. Let's start. But what are the classical formalism of math? You have formalism from Bourbaki with a set theory that builds with substitution, where I can say 2x of r. The idea is that I can rewrite all the instances of x of r and link them with a white square. So it's a powerful tool that is very intriguing for me. That was originally it's not so much used. There are ZFC, there are categories, identities, functors that are quivers. There is the homotopy theory. There is different ways to build the mathematical meanings. What I found a bit disturbing that I would like to explore more is everything is perfect and non-adaptative. I mean, somehow algebra, Arabic algebra, it's fixing, it's casting, it's forcing things to be what we want them to be. So it's make us forget things. I mean, you act with things as if plus and multiplication are two different operators that satisfy some rules. It's possible. I mean, it's a generalization, but it's not the natural way I build when I play with numbers. When I play with number, I can do +1. If I can do if I iterate, if I'm allowed to iterate, I will have sums. I will have multiplication. I will have power, hyperpower, repeat. You can write it as a program. By iterating repeats with instances, with default, you can build what's called hyper operation that explode and very big numbers. So you can construct big numbers with just successor. And you can imagine that if I'm writing my term in a certain way, I can write, put parentheses between the two next terms, and then associativity will be moving the interpretation of, can I do this before this or this? What I would like to do is something that is in the spirit of the substitution, but on the whole level. I mean, I want to be able to replace things by things and to maintain the meaning. So somehow, to build the category theory, one can think it of a quiver, and a quiver is a structure that is built with arrows, which then you forget the direction of the arrow to build what's called the category with the functors, with identity functor, and the object. So you have an object and its identity. The question here is, I want to imagine a quiver where I can zoom in, I can say that my arrow is a quiver, and I can imagine that my quiver could be viewed as an arrow of a bigger quiver. I mean, when we have seen the definition that we had in quant and just before when we had correlation, we seen that we defined things and we found that the definition were incompatible. The definition were incompatible means that we defined the behavior of Alice, we defined the behavior of Bob, and then we've seen that it doesn't work. The question that I would like to take in my project is to start from reality. That it means to start from the experiment. And instead of considering when I reach the limit, you remember when we did the physics experiment, he said, I'm counting, and then there is an object that is reached at the limit, and it is the one that is the reality. So the question is, what if I stop in the middle? What if I allows this to insert breakpoints, and to view things as processes that could be interacted? And the idea is to take only processes that are imperfect. It means that they could be completed to reach non-signaling, so to satisfy the equalities for the line and to have a meaning. And it has also could be restricted to have something that have a meaning. So if I'm between two places that have a meaning, what type of structure can I be? The main problem is the loop problem. I mean, self-reference is will issue a lot of contradictions. And the way we avoid usually the loop problem is the unique fixed point. And the question is, can we do alternative solution? Can I superpose all possible solutions in reasoning? Can I, instead of forcing the unique fixed point, try to define things in another way, to define all things that are possible and to see how they will. What do you mean? If you look at the physical experiments, in fact, the frequency change at each time. So they are looking at this and this and this and this. And the more you do frequency, the more you get observation. And you are saying, I'm trying to reach the reality to understand the phenomena. But one way to represent things is to store the results with a perturbative theory. Note that it's the opposite. I'm saying that the perturbative theory is my real experiment. It's the way that will allow me to define entities. And I want to see how can I define objects from real observation. So for example, suppose that here there is a coloration of an imaginary things where it's either full or empty. And at each time I will have an experiment that have an extra points. So the first time I'm exactly on the middle, the second time I have two views. It's exactly the same that I did in physics with this angle with the sinus, but I'm looking at it discretely. And suppose that I want to store the result. So below the diagonal, I put the blue point of view. And above the diagonal, I put the red point of view. So you see that when I exactly between two places, the blue and the red will never agree. And that each time I'm a multiple of such a thing, it will repeat this inconsistency. Okay, it will disappear if I look as probability, because the number of times, the more measurement I do, the more refined measurement I do, and the more the picture I obtain is precise. But there is a sequence of frequency that still will never behave. So there is a sequence of speeds that will never provide consistent answers from top and from down. So my way to build an object, even if I'm starting from an imaginary perfect object with perturbative, if I want to consider all the objects, is not exactly the same. Should I just use the measure and take the more or less? Or can I do more? Can I play with all the parts? Another example of a drawing process, for me, when I'm drawing a graph, I could be interrupted at any moment. So, for example, if I'm drawing this one, I'm saying that canonically the vertices are numbers. So my way to draw the graph is I'm going from 1 to 2, then from 2 to 3, then from 3 to 4, then I'm raising my hand, then I'm doing this way. So if I want to describe it as an interruptible process, I have to have half edges that are going, and I have to have a notion of time. I am drawing the first vertex, I am drawing the second vertex. So if I define a canonical basis or canonical way to describe, I can represent things. What I want to represent it by is just a sequence of action that will be seen as deviation from a canonical representation. I want to represent everything by a sequence of paths with integers. In the spirit of Bourbaki representing things with a square, what I want to do is everything that is concrete, corresponds to a real experiment, to a real imperfect interruptible experiment, could be represented with a canonical way as a chain of squares. I mean, the question is that connectivity and emptiness are misleading concepts. Why? It's because if it's a concrete object, if you say it is empty, then it's maybe you don't have a zoom that is fine enough. In your experiment, you haven't considered quarks or fermions. You haven't looked in grids of cells of a certain size. And if you are saying it's disconnected, the fact that you interacted with it means that you put things in the border, and you never know, maybe there is a path that you haven't imagined for outside. Maybe you haven't zoomed out enough, and maybe it's connected in a way you haven't thought of from outside. So what I want to do is, instead of saying statements, saying belief in statements, and play with beliefs in statements, but maintain the unitarity. So if you say there is a point here, I say, okay, let's zoom in and look if there is a point. And if you look with a microscope with a grain fine enough, you will be able to insert something. Because ultimately, the atoms doesn't touch each other, so there exists a fine graining that separates stuff. So I can split things if I change my theory. If I'm allowed to have a theory that can rewrite itself, I will be able to split things. A way to view things, what we are doing as a process, or an anthropomorphism, means that I'm someone that is doing things, that interacting with other things that are doing things. I might be doing processes that could be interrupted. I'm computing E, I'm computing pi, I'm computing gamma for another. What I'm doing is I'm using an actual memory, and I'm doing a real process. So I'm iterating, counting, so I'm adding new items at each time. And I'm trying to reach the objective, but I could be close, it could be far. Okay. But in quantum, we have these Hilbert spaces. Where does the Hilbert spaces come from? Where does this freedom space to say that my states live in a Hilbert space and he carries information? So suppose that you have A is equal 0 or B equal 1. If my logical function is either A equal B or A is different of B, in fact, I don't really care about the value of A and B. All what I care is my evaluation of the similarity of them is fine enough. So I moved a property about having a value for A of B to a property of being able to test if it's the same or not the same. So I really don't need to know if they are 0 or 1. It's even worse. I don't need an ontology to define the existence of a state that is as strong as the one that I would need. I mean, I can split things and say, okay, in fact, they live in a Hilbert spaces, in a natural space, and they have components on different direction, and they will be allowed to do rules. And because I don't need the same thing when I'm manipulating function over them than what I need to have the value. So maybe I don't need to know why the Lean user chose this sequence of tactics. Maybe I can think of it as a superposition because I don't care why he chose it. What I care about is to be able to certify that it works. So the model that I need to represent the choice of strategy, maybe I can use something quantum-like. Maybe I can use superposition and saying that I can superpose over some field or over some structure that is more complex. Somehow, we don't need effectively to do the correction. We can ignore in error correction codes. What we need is just to make things agree. Ultimately, being correct is a matter of agreement. As long as I have a voting system that decides what's correct and what is not, I can work with that as a definition of true. So let's look at cases where I have choices that I don't consider. When I'm computing reals, for example, the Fourier algorithm, what I'm doing is what's called fraction continue. It means I'm taking a number and I'm trying to see how rational it is. How do I do that? I take the integer part, and then I invert and I continue. But I can do this with different ways. I can start from my number, and I can start from a little bit left, a little bit more left, or a little bit more right. And I can either add or remove. So I don't need to do the fraction continue the way it's taught with only pluses. I can also choose to switch depending on the direction to build things that are different, but that allows to build the same object afterwards by reconciliation. And I can compose by saying, okay, I have a fraction of my memory that is working, and I'm trying to do a fraction continue computation. And at each time, I can define what I want to do, where I am, and the superposition of possible things. And I can even make them carry things, because I'm viewing them as basis vector of states. At the end, they will collapse, but I don't need them to collapse now. I will allow them to manipulate in order that is information friendly, that without violate inequalities that are of transfer. Okay, I don't need to do fraction continue. I can do just binary writing. There are two things. At each time I need to add someone. Do I start from before or do I start from above? And do I stop just before or do I just stop just after? So there is always these four choices that I can use in computing the next power of 1/2 to the n when I'm or the next larger bit that I can play with. So when I see a circle, the four parts that I cannot distinguish can be seen as a symmetric interactive process of someone who's trying to draw a circle. So if I try to consider drawing a circle, for me what exists are screens that see circle by saying, is there point of the circle here or not point of the circle here? So you can have two ways of representing this type of stair, a weight encoding if the slope is slow, but how many I'm advancing at each step, or a progress in growing where how each step I increase by one and I'm looking to how much I go up. So this type of drawing allows to see sequence of numbers as picture. So I can suppose if I'm on the top left and the same direction is like this, then my picture is of this shape. So I'm reading this sequence as this drawing. So I can associate to any sequence of number a drawing that depends on where I think I am in the process of drawing the circle. But if I'm on the down sides, the picture is not the same, and I have this symmetry because I can't say it's safe from here or it's not safe. So I can have replacing the black by white is another valid way. So there is the P position when I'm going from top, and there is the Q position that is on the. So what I call a third derivative is if someone is born at day t+4, he will believe that it is a circle. But in fact, I do the circle, so I know what I put inside. In fact, either I started from the top and I went to left and I succeeded to reach my points at each time I passed my acknowledgements and I finished drawing, or I started from the left and I went down, or I started from down and right. So there is 8 ways to make my 4 things that are completely, that looks for anyway who's built after the drawing, who was born after the drawing of this thing, is the same object. He has no way to know what I did. But that doesn't deny them the right to be. I mean, I can define objects that are inside the drawing of the circle. I will define possibility of that's when I'm writing with these symbols, it means that I want to point out the possibility of interruption. So inside 1, I will put 4 breakpoints. Why? Because there is 4 ways to cheat an identity. If someone is claiming this is equal to this, they can cheat you by misleading you on the address of the first part you are reading. They can cheat you to mislead you on the address of the second thing that you are reading. And they can cheat you on the reading on the equality and so on. So I can put breakpoints to be able to check the possibility of failure of the procedure, and saying that any procedure that I define as 1, in fact, if I want really to implement it, I will need a bus, a RAM, a transfer. I will need a real protocol that will be decomposed. And if I need a protocol that builds a protocol, I will have the same consequences. So what do I call? It was a derive. Why it's a derive? It's because my belief at the nice model is everything is turning around in spiral like La Voie lactée, and it can go either outside or inside. So when I see I have an arrow above, I can put it in a drawing where I went there and then I went up and then I go back, then I went down on the other side. Or I can put it in an arrow that I went there, I went up and I went there. So I have different way of saying I put an arrow before the D. So the D, it was because I started with the intent of the drawing the circle. Okay, I didn't manage to draw the circle, that I was a bit above. And in fact, I came back. I can also represent when I go horizontally. And now how do I put the 0 versus 1? I am saying that I can put a space for what I know and the space for the position. So I can put the 0 as I'm close from the node 1 and the 1 that I'm above from this one. And I can associate it to concrete internal trajectories that are completely indistinguishable. I can also imagine structure as go and come back. So the question is, can I build this natural part inside the state and saying that even the unity, even the 1, can be thought as a base with natural coefficient numbers. So the idea is that if I want something that I compress, I will regularize. So instead of saying I advance by 1, I can amortize the cost. I'm saying what I look is at the average thing and to advance by 1/4 at each time. And maybe I can have something that's behave like what I expect. Because the more I have precision, the more I'm close to the expectation, the more things collapse and the more I go close to the classical thing. And in the idea of representing things with only paths is possible because you can do things by turning around, by copying on the border. So if I'm D, I think I'm here. If I'm Q, I think I'm here. And I can maintain consistently 2 points without the center and without the infinity, with describing what's inside while. So I am saying maybe I can describe things with paths. Why? Because quantum, what does it say? I mean, my interpretation is that it says between two things observable, you can define paths, but you can define a uniform superposition of paths that could exist. So you can put phases on the paths and imagine a superposition that describes the links between what was and what will be. So, yeah, there is two ways to view, because it's sometimes I view it as northeast and sometimes you view it as north, but it's the same P. And basically, you can, the fact that you consider your lattice as depending on where you put your point of view is somehow below. I'm putting things as I'm saying that the square is a losange, and above I'm saying that the square is a rectangle. It's different point of view, but if you organize them, it's somehow I'm imposing a canonical order of things and a canonical way to describe a sequence of paths that will allow us to define all the injections inside it. I will skip this. What's the conciliation? Yeah. So, for example, if I want to compare with one sequence, I will want to point out where I am, point out the distance. I have a kind of networks, and the procedure is always by pop. I'm popping a new element. And the way to represent it will induce new structures. So if I want to see how I have any map, I can see it as a deviation from the canonical structure. So a sequence of integers. How? But by saying I'm just copying. So if I'm saying, if I want to represent the map that is like this, I can represent it without any edge crossing by taking the number of necessary copies of the second element. So instead of going like this with edges that cross, I say my canonical element, I'm allowed to go from the black edges on the left to the right edges on the right. So I will create enough copy for it to be representable with this type of things. And why quantum with natural is possible, it's because you can always represent with phases. And you can say that the smaller phases require some day to be born. So at the first step, I can only have this small type of phases, and after that, I have, the number of turns depends on time. And I built, you can imagine building conciliation process and imagine relaxing the tensor structure. And in one of the gates, you don't really need complex, you don't really need square root of things. You don't really need, you can play only with plus ones and addition if you have enough space, because somehow you can always say, I can act on the plus state, act on the minus state, and always update them. And yeah, the NP complete problem is the partition, but so I will build things structured slowly by maintaining, do I add in the left, do I add in the right, am I doing a multiplication, am I doing a rescaling? And by alternating this type of things, I have the steps of adding either on the left, on the right, then doing the rescaling to make sense, then going to the stack to the right. Maybe it allows to do things. And if I look to the CNRS, somehow the CNRS, it links a potential things. What I need to do universal quantum computation, what you need to do is the two gates. The Pythagore gates, the one that is here. So if I know to do these two things, and these two things, you can see them as distorting the net. The one is respecting the things, and the second is with distorting the thing, the two basic elements. Because you can move by 4-1 and move by 5-4 is exactly a net distortion, and I think that one can visualize things as quarter of a process, so maintain everything in a quarter plane, and say what happens in this quarter plane. And I will do a superposition of what if I was not in this quarter plane and was in the other. So at each time I can adapt my point of view depending of my point of view at the time step before and depending on the other 3 points of view. And for the C node, you would have positions where I could put things. So I have a creation element. Instead of thinking that the C node is just flipping a bit that exists, it's somehow creating a bit under some condition. So under the condition that I have a free spot, I can apply the C node, which will create a new one, which is linked to the one it copied. So I'm adding extra information than the standard one. And I'm saying maybe you can express now quantum was just distorting net operation. You say, I have this +1 and then move, or I have, it has to be reversible. So afterward, I'm looking like this, so we'll have these 2 positions that are linked. So I could remove it and go this one and apply twice. Yeah, the same with fermions and modes. And yeah, for example, if you have the states alpha 0 plus node 1, you can say that nothing is the dot and the other is the slash. And then you put either I am connecting them directly or I am doing a cross. With at each time the idea is that a variable is in fact 4 variables if I want to work with it. But I need to work with it consistently of the position I put it. So somehow I want to maintain an address point of view, a value point of view, a zoom in point of view, and a zoom out point of view. And what I'm claiming is that I can do view symmetries here, do Lie stuff and to things like the anti-commute here. But at each time I do, I will symmetrize. Below, I'm seeing the B as equational theories, and I'm trying to build at the same time the equalities and the symmetries, and to see if I can recover with this type of things the quantum behavior or approximate the quantum behavior with integrals. There are links. For example, here there is things that similar but not exactly the same that I hope to connect with. For example, one interesting point is that this interactive proof system somehow it's changing the characteristic property and the definition. So for example, if I speak about graph isomorphism is characterized by an interactive protocol. So if I have a localized graph isomorphism, if I have a graph isomorphism protocol, it's equivalent classically to the same. I mean, if the provers are forbidden to share entanglement. Now, if I'm extending, I'm allowing them to share entanglement, and I see it as a definition, I have a new quantity that is called quantum isomorphism. Because now I'm just allowing, I'm taking the characteristic property as definition of a new term. And what I hope somehow is this non-signaling things and the way to define things and the correspondence can make sense if I imagine some notion of locality where I say that someone cannot exchange messages too far, too slowly. So somehow I want to use this quantum type of analysis, but cut it with discrete parts. So it says I can define the cats, I can define the infinite continuity, someplace as bosons, someplace as fermions. Yes, what's this infinity? Yeah, okay. What I wanted to say here, yeah. Somehow what I told you that I have cells, I want to have cells, some parts, I want to have possibilities that look like to the end, it's where the next will arrive. And I have parts that can only be cut because they are protected. I don't have the strength of having it's not the same type of things, but it's things that have only sequences that are built in unary, if you want. So the bosons type of things is boson will occupy sites, but I don't know, they're not identifiable. So I can view them as just sequences of slices of points that are happening, and I want to view them in unary. And yeah, the question is, can I reproduce quantum-like behavior with only natural number? And can I use it to formalize what I have if I remove atomicity? Means the one is reviewed now as one that can be observed with an underlying Hilbert space with possible superposition that are consistent with what I can see. And my space is the same, is any space that is rich enough to accept the closure by the superposition, by the symmetries of the object that I just built from the other side. So this way of building the object, building the projector, building the symmetry, building the unitary, building the Hermitian, and now building the new set to complete with some part that is concrete and some part that is imaginary, is a hope that I have for defining something that is discrete and that approximates quantum. It's a far-fetched project, and it's not. I mean, when I told you that the links somehow, yeah, will not. I mean, I want to view things with two parts that somehow they have anthropomorphism and rigid framework of thoughts, or rigid method of thoughts, but I want to have this pair of things as ontic elements. So it's not a project for you or for the week to stay, but if I wanted to share also a work in progress that is it's linked to things that are there, but it's not yet ready to. It raises just the question of we are seeing quantum. It shows that there is way to interpret, and what I'm trying to say is that maybe we have way to represent it with nets, with other structures, and to re-express what we use to see differently in a consistent way. But nevertheless, if you after this lecture, I will give you the links, and there is one part that is the classical things that are really recommended that are really on the link with homologies and the things that we are considering here, and the very recent projects. The last part and the links with the literature is more sharing a work in progress about how one could try to extend definitions and to reformulate things in the spirit of quantum. But it's not at all something that is a short-term project or things like this. The idea is just, can I reopen the one and put some intents, some things to be, and create superposition by creating breakpoints and by imagining things in a very simple way, not using complex maths, but rethinking tools that could rebuild complex maths inside simple structure. And the links were more with the second set of papers. Yeah. Here the links for inflation and causality. It means that by looking at these classical things with causality, I can imagine inflation and provoke creating a sequence of correlation that goes beyond the quantum. Locality, it means that if I defined a model where people are in sites and the communication is between people that have to respect some networks, I obtain new notion of things and new complexity, sometimes for which quantum cannot help, sometimes quantum can help, but it helps to see things in which we maintain the domain and see quantum in this framework. Concrete math is because it's a way to rephrase the equation with the polynomials, and the way I do things is close, but I want to add an orientation before having this rewriting terms. It's just close because it's using concrete methods. I put it. No, I will not go to it now, but so that's what I wanted to share. So yeah, thank you. Other questions? Yeah.
I have you of the idea, for example, doing work we do mathematics or the summation of the axioms and the axiom choice, and at the same time doing mathematics without the axioms, for example, and compare both result class simply with.
Yes. The idea is to look in terms of you have a framework and you have another framework, and for me, what's interesting as superposition is look at all the paths that leads to something, and to see, can I define things by looking at this model leads to this path and this other leads to this path, so there are both ways to build this element. So for me, what I want to see as superposition is it's like you have imagine you have a metric and you need to look at the superposition over all the completion toward the proof. So I will look at I'm restricting myself at some family of formalism, and I'm saying the formalism that needs 2 to the n proofs to read these steps are equivalent. So I want to see if I can define a space over them and to maintain this idea of at each time that I have something, I will look at the way to extend and the way to cut that makes sense. And to say maybe I can play with the space and add it as a module. I mean, so if you see it as I have a way to do a proof, I'm using this choice of strategy, but maybe with another axiom, I have another path. For some problems, this axiom will help, for others, that doesn't. In terms of, it's, for example, if you take a graph, and if you like what the table said, I mean, you are looking for points that doesn't have any edge. If instead of having the graph, you have 2 copies of the graph and the strong product, your stable, you can copy them and you have also the same type of phenomena, but you will have new stable that emerge. And these are the type of things that are used as one state in the quantum, but by taking infinite copies. For the way I see it is that the quantum analysis take the object, take infinite copies, and says, okay, this is my state. And I will amortizing by taking the square root of the n. I mean, I have the way to estimate the cost that it would have taken if I repeated it n times. And what I find very intriguing is that if instead of repeating it n times, I say, okay, but I have patches of size d, and I repeat only by patches of size d, the quantities changes in terms of communication and non-signaling. And so the property is not exactly the same if I'm really looking as a concrete process and not saying that this infinite object exists, but I want to give a meaning. I mean, I want to give an operational meaning. In terms of expression, what I was saying, maybe I skipped something. It's if I want to describe all mathematical expressions. So I'm saying all mathematical expressions are well-parenthesized expressions. and my wheels are just, I'm trying to do a parenthesis, but I haven't finished. So, and I'm doing even worse. I'm saying I'm interested only on things that are not well parenthesized and that don't have a unique way to change it to a well parenthesized expression. So I'm looking at in any environment that is like this. This is a soft spot to insert a mathematical universe. Because there will be no confusion on anything else. It's completely separated from the left, completely separated from the right. So if I want to put a universe, this is the point. So if I see this is at the x that I split it in two, this is the point where I would like any equational theory will fit here perfectly, because it will contradict with nobody. Now suppose that to fix my things, I have this thing. I will need n parentheses. So it's projected to the left too much. So I will look at the possible completion and where I can put what are the, I want to characterize things like this, and I'm saying these are environments in which math can live. What is math? Is people that say that I have equalities and I can play with them and they are universal. So they have to not interact with other stuff. So if I'm saying I'm interested only on completion with n parentheses at most in the left, I can achieve step dual things where I'm saying I look to fixing the thing that requires n splices, and I'm to the one that requires only one to fix. And inductively, we say, okay, now I fixed the extreme terms. Now all the terms that require fixing are the terms that requires adding two steps. Because I did this and this and this, and I spent 3 times to do my parentheses. In fact, I'm drawing this thing. I'm drawing very precisely the arc. I'm trying to draw a circle, okay, but I'm inside the process and someone spoke to me in the middle and I stopped. It's still a real thing. So it should be formalizable even though it's not a finite thing. I mean, my program got interrupted. It doesn't have meaning, but my memory is full. So there are bits in my memory. So I want to speak about bits in my memory, even if the power was shut. And then I'm saying, okay, but tomorrow you are using a frequency of 10 mega, and there's a new computer that is going at 20 mega. So when I was saying I'm trying to draw the picture, what I want to say is that at each time, my belief is I have a quadrant, and what I want to say is there a picture here or no, and how confident I am in this. And this is the thing that I'm supposed to answer. I always suppose that I'm top left, and I'm building a belief, and I'm saying I'm updating my belief because I'm not the only one in the universe, so I'm exchanging with other people who has other beliefs. And the other people has other beliefs. They are saying me, oh no, there is no picture, but what's the resolution now? So I have different arguments that are evolving in time space. I mean, I have the net that I'm building, the belief that I have because I force it to project and to say either I have a pixel, I don't have a pixel. I have the resolution because now they are asking me, yeah, if I look at this, is there a picture? Okay, I'm saying that there is a canonical way. I can always cut in 4 and define 4 types of process. Process that I think that are top west, they are here and they are here, and I'm adding something that they don't need to completely agree. I don't need to be restrictive as Poincaré. I don't want to have a pre-shift condition. I want only to have a error correction code condition. I want to have a mitigation process that says, okay, if this one says yes, and this one says yes, and this one says yes, then maintain your belief. In error correction, we have something that's called message passing. And it works perfectly if you have node cycles. Each node needs just to remove his old belief and to add the sum of the beliefs of the other, if you are looking with in the logs picture, and with the products, if you are looking on the opposite picture with probabilities. The thing is, if you apply these type of things in concrete life, the maxint is here. And with maxint, you have another thing that you need to realize, that in practice, we do the heuristic and we play with changing things. But what I'm saying is it should make sense to quantify these beliefs and to say that ultimately I don't need the reality to exist. I just need a consensus to exist, and they will be happy with it. And they will be able to manipulate it more freely because it will have less restrictions. But I agree, it's really extrapolative, and it's not something. It's not something built. It's more a project. Can we use this notion of quantum, this notion of existential superposition, that I'm not required to be either alive or dead, as long as I behave well with the measurement? I can define this notion, and it's perfectly fine with information theory. So why not try to define interruptible process? Because in reality, processes are interruptible. So the errors, instead of saying it's something that I should avoid and I should do math only with rigid things, maybe I can look at only at things with error and look at what are the good in mathematical environment, because it's easy to put things. I mean, if you can restrict enough to have a place for math. I have different places for math. I will have different places for lean, for things like this. And I can try to think either of having everything that is the same, or to look if there are ways to make them talk together and change each other and evolve in a different way. Somehow, can I imagine a Turing machine that are allowed to act on its automata? Would it say the same thing? It's not obvious. I cannot say to you, I know that it is completely different. I know that it's the same. It depends on your measure and depends on the way to see things. Okay. So thank you. Yeah. There's no more question. So yeah, about the different things, if you want to read the other papers or things like this, you have you can contact me by mail and can discuss.
Yeah, it's true. We will not picture.